Number 1. The Lycurgus Cup. Picture a Roman chalice from the 4th century AD. When you light it from the front, it appears opaque and pea green. Walk around to the other side and shine a light through it, and that same glass turns a deep translucent blood red. For centuries, nobody could explain the shift. Then, in 1990, researchers at the British Museum placed a fragment under a transmission electron microscope. What they found was extraordinary. The glass was infused with nanoparticles of silver and gold, ground down to approximately 70 nanometers in diameter. That is roughly 1,000th the width of a grain of salt. At that scale, the particles interact with light through a phenomenon called surface plasmon resonance. The metal nanoparticles scatter shorter blue and green wavelengths while allowing longer red wavelengths to pass through, which is why the cup looks green from one direction and red from another. The precision required to achieve this is remarkable. The silver to gold ratio sits at approximately 330 parts per million. Silver to 40 parts per million gold. Any significant deviation from that ratio produces muddy, non-shifting glass. The consistency of the effect implies that this was not a lucky accident. It points to a specialized guild of Roman glassmakers who had mastered exact heating and cooling cycles through generations of empirical repetition. The cup itself is classified as a diatretum, or cage cup. The outer decorative cage was not glued or attached. It was carved from a single solid block of glass, an extraordinarily delicate technique where one slip of the tool would shatter the entire piece. The scene depicted on the cup shows King Lycurgus being strangled by grapevines, and the color shift from green to wine-red mirrors the transformation of grapes into wine. The cup literally performs its own subject matter. It was almost certainly commissioned for the highest levels of Roman society, a prestige object meant to demonstrate total mastery over the natural world. And it is the only complete example of a dichroic diatretum known to exist anywhere in the world today. Here's what makes this genuinely unsettling for historians. This level of deliberate nanoscale light manipulation did not reappear in the human record for over 1,000 years. NASA scientists independently developed similar dichroic coating technology in the late 20th century for satellite mirrors and astronaut helmet visors. Medieval glassmakers tried to produce color-shifting effects using copper or iron oxides. They got red glass. They never got glass that changed color depending on the direction of light. The techniques were passed through master-apprentice lineages, closely guarded, and never written down. When the Western Roman Empire collapsed in the 5th century and the supply chains for high-purity gold and silver broke down, the knowledge vanished with them. The mainstream scientific view holds that the nanoparticle suspension was achieved through controlled high-temperature colloidal chemistry, reproducible in principle. The historical perspective emphasizes that the guild system preserved empirical recipes refined across generations without any theoretical framework for nanoscience. And then there is the speculative edge. The precision of that metal ratio at parts per million levels implies measurement and quality control capabilities beyond what most historians currently attribute to the 4th century. Modern science still cannot fully explain how Romans achieved molecular level precision without thermometers, spectrometers, or any known quantitative instruments. They were engineering the interaction between matter and light at a level humanity would not approach again until the space age. The Lycurgus Cup is a physical record of a technological peak that was mastered and then completely forgotten. And it will not be the last one on this list. Number 2. The Iron Pillar of Delhi. Here's a straightforward anomaly. A 6-ton, 23-foot-tall column of raw iron has been standing outdoors in Delhi's monsoon climate for over 1,600 years, and it has virtually no corrosion. That should be impossible. Iron rusts. That is what iron does. But the chemical key lies in something unusual about this particular iron. It contains an abnormally high phosphorus content, a substance modern steelmaking deliberately removes because it makes steel brittle. In the pillar, that phosphorus does something remarkable. It catalyzes the formation of a dense, stable protective film called mesowite, which is iron hydrogen phosphate hydrate. This mesowite layer is only about 1/20th of a millimeter thick, but it is completely impermeable, sealing the iron core from oxygen and moisture. And it is self-healing. If the surface is scratched or chipped, the exposed iron reacts with atmospheric moisture and the embedded phosphorus to regenerate a new misoite layer automatically. The pillar was not cast as a single piece. It was built up layer by layer through forge welding, where individual white-hot lumps of iron were hammered together. You can still see the hammer marks on the surface where individual pieces were fused, with slag physically squeezed out at each joint. This was created during the 4th century AD, under the Gupta dynasty, widely regarded as a golden age of Indian mathematics, astronomy, and applied chemistry. The tradition behind it, called Rasa Shastri, was an ancient Indian science of minerals and metals. Practitioners were essentially early applied chemists who understood how specific ores interacted with specific fuel types. The smelting was done with charcoal, which allowed a slow, controlled chemical exchange that preserved the phosphorus. Modern coal-based smelting introduces sulfur, which completely destroys the protective effect. A solid wrought iron column of this size and weight would not be matched anywhere in Europe for another 1,000 years. The pillar was erected as a dvalya, a sacred standard for the god Vishnu and a victory monument for Emperor Chandragupta II. And the technology was not confined to a single monument. Similar iron was used as structural beams in the Konark Sun Temple and temples at Puri, beams that have survived 800 years of salt air, confirming the tradition was consistent and replicable across sites. Researcher R. Balasubramaniam at IIT Kanpur proved definitively that the pillar's durability was a deliberate result of ancient metallurgical technique, not an accident. The mainstream explanation is clear. Phosphorus-rich ore combined with charcoal smelting creates the misoite passivation layer as a predictable chemical outcome. The historical view emphasizes the Rasa Shastra tradition as a systematic empirical science of ore and fuel interaction, transmitted through guild lineages over centuries. The speculative angle pushes further, suggesting the degree of corrosion resistance implies Gupta-era smiths had a working understanding of passivation chemistry that modern science associates with 19th century electrochemistry. The irony is sharp. Modern industry treats phosphorus and slag as defects to be purged. Ancient Indian smiths treated them as essential protective components. When the British arrived and imposed coal-based smelting, the traditional charcoal guilds and their orally transmitted technical knowledge died within decades. Contemporary metallurgists today struggle to achieve equivalent longevity without expensive modern additives like chromium or nickel, the ingredients of stainless steel. The pillar was built to serve as a permanent record of imperial triumph, and it has done exactly that for over 1,600 years, outlasting every structure built around it, using nothing but its own internal chemistry. But not every lost technology left behind a physical monument. Some left no trace at all, except in the bodies and memories of the people who practiced them. Number 3, Polynesian wave navigation. This is a dramatic shift in scale. We go from a single iron pillar to 1/3 of the Earth's surface. Polynesian navigators settled nearly 5 million square miles of open Pacific Ocean without any navigational instruments. No compass, no sextant, no charts. The primary tool was the deep sea swell, long, low waves generated by distant storms that travel across entire ocean basins without changing direction. These swells form the ocean's permanent background signal. A master navigator sitting in the hull of a canoe could feel the pitch and roll of a swell only a few inches high amidst the chaotic noise of surface waves. They identified invisible land by reading how deep ocean swells bend around islands, creating unique interference patterns. Waves curving toward land through refraction or bouncing back from coastlines through reflection allowed detection of islands from distances up to 50 miles away. The star compass system divided the entire horizon into houses based on the memorized rising and setting points of hundreds of individual stars. Marshallese navigators developed 3 distinct types of stick charts: Matang, which were teaching grids, Rebelib, which mapped entire island chains, and Meadow, which charted localized currents. These were constructed from palm ribs and cowrie shells. But here's the critical detail. Stick charts were never carried on voyages. They existed solely as land-based teaching aids to ingrain wave and current patterns into long-term memory. Master navigators called Palu began training in early childhood, culminating in the PWO initiation ceremony after years of apprenticeship. The knowledge lived entirely in the navigator's body and mind. The proof came in 1976. A reconstructed Hawaiian double-hull voyaging canoe called the Hokulea sailed 2,500 miles from Hawaii to Tahiti using only traditional navigation methods. No compass, no charts, no GPS. The navigator was Mau Piailug, a master wayfinder from the island of Satawal in Micronesia, who guided the canoe across open ocean without a watch or any written logs. The successful arrival demolished the Western academic theory, promoted by Andrew Sharp and others, that the Pacific was settled by random accidental drifting. Early voyagers had deliberately sailed against prevailing trade winds so they could return home quickly with the wind if no land was found. That is a calculated risk management protocol. Mau Piailug noted that certain deep water swells were only detectable during specific lunar phases, knowledge that very nearly died with him. The mainstream view holds this was systematic empirical science accumulated over thousands of years of trial, observation, and oral transmission. The historical perspective sees the navigational tradition as implying a sophisticated pedagogical infrastructure and knowledge-sharing network spanning thousands of miles of open water. The speculative fringe proposes that master navigators possessed a form of heightened proprioceptive or magnetoreceptive sensitivity that modern populations may have lost through generations of technological reliance. The arrival of European sextants and paper charts made sensory navigation training appear obsolete. Younger generations stopped learning. Detecting land through the specific vibration pattern of a canoe's keel is among the skills that are nearly impossible to recover once the unbroken chain of oral transmission is severed. The Hokulea voyages sparked a cultural renaissance across the Pacific, reconnecting modern islanders with their navigational heritage and identity. From reading the ocean to pouring stone that heals itself. Number 4. Roman concrete. Here is the central contrast. Modern Portland cement degrades in 50 to 100 years. Roman concrete structures remain structurally sound after 2000. In 2023, MIT researchers published a breakthrough. They discovered that Romans mixed quicklime directly with volcanic ash and water at extremely high temperatures, a process called hot mixing. Those small white mineral chunks found scattered through Roman concrete, which scholars had previously dismissed as evidence of sloppy, incomplete mixing, turned out to be reactive calcium reservoirs called lime clasts. When microscopic cracks form, rainwater or seawater dissolves those lime clasts, which then recrystallize inside the fissure, sealing it automatically. The material heals itself. There is a second mechanism at work in marine environments. Saltwater reacts with the volcanic ash to produce a rare mineral called aluminous tobermorite, a crystal that actually strengthens concrete over time. These tobermorite crystals grow over centuries, interlacing through the material like a structural web, continuously increasing compressive strength. Ancient harbor structures that have been submerged for 2,000 years have been measured as stronger today than when they were originally poured. The core ingredient was pozzolana ash, a specific volcanic ash sourced primarily from the Bay of Naples near Mount Vesuvius. This was not optional, it was irreplaceable. The ash gave Roman concrete its hydraulic properties, meaning it could set and harden even when fully submerged in seawater. Romans built wooden formwork underwater and poured concrete into it. That pourable hydraulic quality also allowed monolithic construction, the creation of single continuous stone masses rather than stacking individually carved blocks. The Pantheon's dome spans 43 meters with 0 internal support beams. Engineers managed the weight by using heavy basalt aggregate at the base and porous pumice aggregate at the top. The baths of Caracalla, the markets of Trajan, these massive interior spaces were only structurally possible because of continuous poured concrete vaults. Roman architects carried standardized technical manuals across the empire to ensure a bridge in Britain met the same specifications as a temple in North Africa. The mainstream explanation centers on the 2023 MIT study. Hot mixing with pozzolana ash and lime clasts explains the self-healing cycle as reproducible chemistry. The historical view emphasizes Roman engineering manuals that codified a tradition focused on multi-generational durability over construction speed, a fundamentally different design philosophy from modern building. The speculative position argues the Romans understood a broader set of mineral-water interactions we have only partially reconstructed, and that the full recipe may involve variables not yet tested. The technology was lost when Mediterranean maritime transport networks collapsed in late antiquity, severing the supply of pozzolana ash from the Naples region. Hydraulic cement was not independently rediscovered for 1,300 years, one of the longest technological gaps in the built environment record. Medieval Europeans who could not replicate Roman construction concluded the ruins must have been built by literal giants. Knowledge loss distorts even the understanding of what was lost. Modern Portland cement production accounts for approximately 8% of global carbon dioxide emissions, and engineers are now studying Roman methods as a path to dramatically lower carbon construction. Number 5. Greek fire. In 673 AD, the Byzantine Empire faced an existential crisis. Arab fleets were closing on Constantinople. A refugee named Callinicos of Heliopolis arrived in the capital carrying a formula that would change the balance of power in the Mediterranean for 500 years. Greek fire was a liquid incendiary that burned with extreme heat, and seawater intensified the reaction rather than extinguishing it. It was deployed through a pressurized bronze pump mounted on ship prows, functioning mechanically like a modern flamethrower. The stream exited the nozzle with a roar described in multiple contemporary sources as sounding like thunder, a psychological weapon layered onto a chemical one. The leading hypothesis proposes a base of crude oil, naphtha, mixed with pine resins for adhesion and sulfur for sustained combustion temperature. A controversial but persistent theory suggests quicklime was used to trigger spontaneous ignition on contact with seawater. Historical accounts consistently state it could burn beneath the water's surface, implying a chemical component that supplied its own oxidizer, but no confirmed candidate has been identified. It clung to wooden hulls and fabric clothing, nearly impossible to scrape or wash off once ignited. Contemporary sources record only 3 reliable extinguishing agents: large quantities of sand, strong vinegar, or urine. It allowed the outnumbered Byzantine navy to incinerate entire attacking fleets before they reached Constantinople's sea walls. For 500 years, it functioned as a strategic deterrent, blocking multiple caliphate expansions into southeastern Europe. The secrecy protocols were extraordinary. No single person or family knew the complete formula. One lineage refined the naphtha, another built the bronze siphon pumps, a third mixed the chemical additives. Emperor Constantine VII's official treatise claimed the formula was revealed by an angel to the first Emperor Constantine, state propaganda wrapped around state secrecy. Every warship required a specialized engineering team to manage volatile chemical stores and maintain airtight bronze seals under combat conditions. The mainstream view describes a naphtha-based incendiary with resin binders and sulfur, pressurized through engineered bronze siphons. The historical perspective holds that the compartmentalized knowledge structure implies a more complex multi-component formula than any single modern reconstruction captures. The speculative edge suggests that the consistent accounts of underwater burning point to an unidentified oxidizing compound or self-sustaining exothermic reaction achievable with 7th century materials but not yet replicated. In 1204, Western Crusaders sacked Constantinople during the Fourth Crusade. The city's infrastructure was looted, and the guild families holding different fragments of the formula were scattered or killed. By 1453, when the Ottoman Empire besieged Constantinople for the last time, the Byzantines had lost the formula entirely and could not deploy their most famous weapon. Modern napalm achieves similar surface effects using synthetic materials, but attempts to recreate Greek fire using only documented 7th century ingredients consistently fail to replicate the adhesive and underwater burning properties. Greek fire was the Byzantine Empire's chemical insurance policy for 500 years, and its loss is a case study in how compartmentalized secrecy becomes fatal vulnerability the moment institutions collapse. Number 6. Wootz Steel. A Wootz blade could slice a silk veil in midair and shatter a standard iron sword on impact without taking a notch. This steel was developed by the Chera, Chola, and Pandya dynasties as early as the 6th century BC in South India, making it among the oldest high-carbon steels in the world. The distinctive wavy lines visible on a polished Wootz blade, often called the water pattern, are the surface expression of an internal crystalline microstructure running through the steel's core. The process involves sealing high-purity iron ore together with the wood and Cassia auriculata leaves inside clay crucibles, then heating them in a pressurized, oxygen-free environment sustained for several continuous days. Inside those sealed vessels, iron slowly and precisely absorbed carbon from charred plant matter through an extremely controlled diffusion process. When researchers John Verhoeven and Alfred Pendray examined surviving blades under electron microscopy, they discovered something startling. Carbon nanotubes and cementite nanowires distributed within the steel's microstructure. The critical secret ingredient was natural trace amounts of vanadium found specifically in Deccan Plateau iron ore. The vanadium seeded the growth of nanowire structures that gave the steel its extraordinary combination of hardness and flexibility. The resulting material was hard enough for a razor edge, yet flexible enough to survive repeated stresses of cavalry combat. The Urumi, a flexible whipsword made from Wootz that could be repeatedly coiled and snapped without fracturing, was an extreme demonstration of its properties. South Indian smiths were manipulating material architecture at the molecular scale over 2,000 years before molecules were scientifically defined. This was not artisan curiosity. Wootz was a primary high-value export commodity that brought Roman gold and Mediterranean wine into Indian ports. Massive manufacturing centers operated across Tamil Nadu and the Deccan Plateau, producing steel for both domestic military use and international trade. In the 1800s, Michael Faraday studied Indian steel extensively and failed to replicate either the water pattern or the internal mechanical properties. The mainstream explanation holds that the nanostructures are an emergent result of specific ore chemistry, particularly vanadium traces, combined with slow crucible cooling under controlled atmosphere. The historical view emphasizes that the Smiths had deep empirical mastery, transmitted through guild lineages, and could read the color of the fire to judge temperature and carbon uptake. The speculative perspective argues the precision and consistency of the nanostructures imply a lost empirical framework for understanding material behavior at scales we would now call nanoscale. Not theoretical physics, but a functional equivalent achieved through centuries of systematic refinement. The technology was perfectly tuned to local soil and ore chemistry. Once specific vanadium-bearing ore deposits were exhausted, the characteristic water pattern stopped appearing. Then, the British East India Company banned local Indian smelting operations in the 19th century to eliminate competition with British industrial steel. Knowledge that had been transmitted through hereditary lineages, practitioners who judged crucible conditions by fire color, sound, and timing, was killed within a single generation. Despite comprehensive modern analytical data on the composition and nanostructure of surviving Wootz samples, scientists still cannot replicate the exact internal structures using traditional raw methods and period-appropriate technology. Number 7. Nabataean water management. Petra receives less than 6 inches of annual rainfall. 150 millimeters, yet it supported a permanent population of 30,000 people at its peak. The Nabataeans built an interconnected system of over 800 underground cisterns and terracotta pipes, a hydraulic network hidden within cliff faces and solid bedrock. They developed a waterproof plaster of lime and volcanic ash that actually hardened when exposed to water, a form of hydraulic cement. Reservoirs were kept underground and tightly sealed to prevent both evaporation in desert heat and bacterial contamination. Terracotta pipes were laid along cliff faces, maintaining a steady downward gradient of exactly 4 degrees, measured and maintained over miles of pipeline. If the angle exceeded 4 degrees, water pressure would burst the pipe joints. If it was any shallower, water would stagnate, and silt would accumulate and block the flow. This angular precision allowed them to move water from natural springs up to 5 miles away using gravity alone. No pumps, no moving parts. They engineered small dams that broke the destructive momentum of violent desert flash floods while simultaneously capturing the water for long-term storage. The same channel infrastructure handled dry season moisture collection and winter storm flood control, 2 problems solved by one network. Cisterns were not rough pits, but precisely engineered chambers carved directly into solid bedrock with smooth, sealed interior surfaces. And despite extreme water scarcity, Petra featured lush gardens, open-air pools, and year-round decorative fountains, a deliberate political display of environmental mastery. Modern aerial LiDAR scanning has revealed thousands of previously unknown channels and terrace systems completely invisible from ground level. By providing water and protection on the frankincense and myrrh trade routes, the Nabataeans charged heavy transit taxes. Water control was their primary economic weapon. A formerly nomadic people became one of the wealthiest kingdoms in the ancient Near East by controlling water where no one else could. The mainstream explanation describes brilliant empirical hydraulic engineering adapted to extreme arid conditions through centuries of iterative refinement. The historical perspective emphasizes that the scale revealed by Lidar implies a far more centralized and technically sophisticated state bureaucracy than previously assumed for a people traditionally described as nomadic. The speculative view argues the Nabataeans possessed a systematic understanding of desert watershed dynamics that rivals modern computational hydrology. After Rome annexed the Nabataean kingdom in 106 AD, specialized labor was redirected to other imperial priorities. Without constant maintenance, channels silted up and earthquakes fractured the aqueduct network. Once the knowledge to locate and repair the hidden underground infrastructure was lost, the population dwindled and the desert reclaimed Petra. Number 8. The Cosmic Engine. In 1088 AD, the polymath Su Song completed construction of a massive water-driven astronomical clock tower in the Song dynasty capital of Kaifeng. It stood approximately 40 feet tall and was the most advanced timekeeping device in the world for nearly 3 centuries. The tower contained a liquid-driven escapement mechanism, mastered hundreds of years before any European clockmaker achieved a mechanical equivalent. It also utilized the earliest documented endless power transmitting chain drive, a mechanical principle now fundamental to bicycles, engines, and industrial machinery. Su Song solved the critical problem of mechanical drift by using a smaller regulation tank with an overflow notch to maintain perfectly consistent water pressure, feeding the main wheel. A 36-bucket water wheel rotated exactly 1 notch per bucket cycle each time a single bucket reached a precise threshold weight. At the summit, a massive bronze armillary sphere rotated in real time to track the movement of visible stars. Carved wooden figures emerged from doors at programmed intervals to strike gongs or hold plaques, announcing the hour, mechanical automation centuries before European cuckoo clocks. Accurate astronomical timekeeping was a matter of state legitimacy in Song China. Correctly predicting eclipses confirmed the emperor's mandate of heaven. Su Song applied knowledge from his botanical studies to prevent bronze gear components from seizing in Kaifeng's humid subtropical climate. The use of water as the primary power source was a deliberate philosophical choice, aligning the machine's motion with the Confucian ideal of nature's continuous flow. The cosmic engine predated European Renaissance-level mechanical complexity by several hundred years. Then came the Jingkang incident of 1127. Jin dynasty invaders captured Kaifeng and attempted to disassemble the tower for relocation to their own capital. They could not reconstruct the interconnected gear system. The specialized engineers who built and maintained it were either killed during the siege or refused to cooperate. Su Song's original technical drawings and engineering notes were hidden or lost during the Song court's chaotic military retreat southward. By the 16th century, only 400 years later, Chinese court officials were reportedly amazed by European mechanical clocks, entirely unaware their own civilization had mastered identical principles centuries earlier. The mainstream view holds that the cosmic engine represents the documented peak of Song dynasty hydromechanical engineering, fully explicable within known physics. Joseph Needham's famous question about the Great Interruption asks why China's mechanical sophistication stalled before industrialization, and the cosmic engine is Exhibit A. The speculative angle argues a broader and older tradition of Chinese precision mechanics existed that was systematically lost during violent dynastic transitions. Number 9. The Antikythera Mechanism. In 1900, Greek sponge divers exploring a Roman-era shipwreck at a depth of 45 meters off the island of Antikythera pulled up a lump of corroded metal they initially mistook for rock. It turned out to be the most complex mechanism known from antiquity. At least 30 interlocking bronze gears carved with microscopic precision, all fitting inside a wooden case roughly the size of a shoebox. A single hand crank drove the entire assemblage, producing simultaneous mathematical outputs on multiple front and rear dials tracking the sun, the moon, and all 5 planets visible to the naked eye. The mechanism combined 2 different rotational speeds into a single output through differential gearing, a principle historians once believed was first invented in the 16th century. A pin and slot mechanism created variable speed output that mechanically reproduced the moon's elliptical orbit, accounting for its apparent acceleration and deceleration. Spiral dials on the rear face tracked the 223-month Saros cycle to predict the timing and even the expected color of solar and lunar eclipses. It also tracked the 4-year cycle of the Pan-Hellenic Games, including the ancient Olympics. 21st century microfocus X-ray scanning revealed thousands of previously hidden Greek characters inscribed on interior gear surfaces, a built-in instruction manual invisible to the naked eye. The hidden text described heliacal risings and settings of specific stars, observational data essential for maritime navigation and agricultural planning. Scholars believe the device originated from the island of Rhodes, home of the astronomer Hipparchus, or followed the mechanical traditions attributed to Archimedes of Syracuse. Triangular gear teeth were individually hand-cut from cast bronze sheet, requiring extraordinary manual dexterity combined with mathematical precision. Modern CT scanning discovered a main drive wheel with 4 previously undetected planetary gear trains mounted on its reverse side, revealing the device was even more complex than anyone realized for over a century. The mainstream view holds this as the peak of Hellenistic astronomical mechanical engineering, building on the mathematical work of Hipparchus and the mechanical traditions of Archimedes. The historical perspective notes that a device this sophisticated implies a broader tradition of Greek precision mechanics that left almost no other surviving physical evidence. The speculative view argues the mechanism requires a longer developmental lineage of prototypes than the archaeological record currently supports, suggesting an entire lost tradition of Greek computational devices. No mechanical device discovered anywhere in the archaeological record matches the Antikythera Mechanism's complexity for the next 1,500 years. As Rome prioritized practical civil engineering over theoretical science, the specialized workshops capable of producing such devices likely vanished without successors. The ship was probably transporting looted Greek treasures to satisfy Roman aristocratic demand, and the mechanism survived only because the ship sank before reaching its destination. If that wreck had never been found by those sponge divers, we might never have known that ancient Greeks could build gears this small, this precise, or this conceptually revolutionary. Number 10. Persian Windcatchers. The final technology on this list closes on the theme of elegant simplicity, doing more with less. Windcatchers, known in Persian as badgirs, operate simultaneously on 2 physical principles. The first is Bernoulli's principle. Faster moving air passing over the tower top creates a low pressure zone that draws air through the system, while high pressure on the windward face forces cool air down the intake shaft. The second is the stack effect. As tower walls absorb solar heat during the day, hot interior air rises and exits from the top, drawing fresh, cooler air through lower openings, creating a continuous passive convection loop. Traditional mud brick construction provides extremely high thermal mass, absorbing desert heat during the day and releasing it slowly overnight, stabilizing interior temperatures. Windcatchers were commonly connected to qanats, ancient underground water channels, so that incoming air passed over cold subterranean water before entering living spaces. This combined airflow and evaporative system powered sardabs, underground basement rooms that remained comfortable even when exterior temperatures exceeded 40 degrees Celsius or 104 degrees Fahrenheit. The tower pushes cool air downward when there is active wind and pulls hot air upward by convection when the air is still, functioning continuously in both conditions. Architects adjusted tower height, shaft dimensions, and opening orientations based on weather. Local winds were unidirectional, as in the desert city of Yazd, or variable, as on the Persian Gulf Coast. Ancient architects could tune a specific structure to its individual plot and local wind patterns through observational knowledge accumulated over generations, knowledge that resisted written codification. Modern computational fluid dynamics simulations demonstrate that traditional windcatchers are frequently more efficient at cooling large air volumes than mechanical HVAC systems in comparable settings. They function continuously 24 hours a day, 365 days a year without consuming a single watt of electrical energy. Yazd, one of the oldest continuously inhabited cities on Earth, depended entirely on this integrated management of airflow and water for survival across millennia. The mainstream view is that the physics is well understood, empirically optimized over centuries of trial and observation. The historical perspective holds that the site-specific tuning represents a form of applied environmental science that resists translation into universal building codes. The speculative view argues the sophistication of regional microclimatic calibration implies a lost empirical discipline of environmental engineering that modern computational fluid dynamics is only now beginning to match. The arrival of cheap electricity and mass-produced mechanical air conditioning made the maintenance of large earthen shafts seem unnecessary. Modern concrete and glass lack the thermal mass of sun-dried mud brick, so building a traditional windcatcher from contemporary materials dramatically reduces its effectiveness. The subtle site-specific tuning knowledge was severed when mechanical air conditioning became the default standard. The last generation of master builders died without successors, but contemporary architects are now integrating windcatcher principles into high-rise buildings in Dubai and sustainable projects across Europe to reduce HVAC carbon footprints. So, what connects all 10 of these? The patterns of loss are remarkably consistent. First, oral tradition as a single point of failure. Wootz Smiths reading fire color, Polynesian navigators memorizing star houses, Persian architects tuning airflow by sensory feel. None of it was written down. Second, supply chain dependence. Roman concrete died when pozzolana ash shipments stopped. Wootz failed when specific vanadium-bearing ore was exhausted. Third, deliberate colonial suppression. The British East India Company banned Indian smelting. European instruments displaced Polynesian sensory navigation within a generation. Fourth, compartmentalized secrecy as catastrophic vulnerability. Greek fire's formula was distributed across multiple families, and when Constantinople fell, no single survivor held the complete recipe. Fifth, the maintenance trap. Nabataean pipes required constant desilting. Windcatchers need regular earthen repair. Susong's clock demanded daily skilled recalibration. Conquest accelerates all 5 patterns simultaneously. The Jingkong incident destroyed the cosmic engine's engineers, its blueprints, and its institutional support structure in a single military event. Technologies calibrated to local conditions are inherently non-transferable. Wootz needed vanadium-specific ore, windcatchers needed site-specific mud brick and local wind data. And there is a recurring irony. Modern industries drive toward material purity, removing phosphorus, standardizing aggregates, actively destroys the properties that made ancient technologies work. The rediscovery gaps are staggering. 1,300 years for hydraulic cement. 1,500 years for differential gearing. Over a millennium for dichroic nanotechnology. Medieval Europeans who could not replicate Roman construction concluded the ruins were built by literal giants. Knowledge loss distorts even the understanding of what was lost. The modern advantage is not smarter individuals, it is more robust, though not invulnerable, knowledge storage and distribution infrastructure. Consider our own vulnerabilities: proprietary corporate knowledge, classified military research, digital format obsolescence, concentration of expertise in shrinking specialist populations. What technologies might we currently be losing without recognizing it? But the ancient world is not just a subject of historical curiosity, it is an active, underexploited engineering resource. Portland cement production generates roughly 8% of global carbon dioxide emissions. MIT researchers are actively developing self-healing concrete formulations based on Roman hot mixing and lime class principles. If modern concrete could repair its own microcracks the way Roman lime clasts do, infrastructure replacement cycles and their associated carbon costs would drop dramatically. Understanding how Roman harbor concrete actually strengthens in seawater has direct implications for coastal infrastructure facing accelerating sea level rise. Sustainable architects in Dubai and Europe are incorporating windcatcher airflow principles into modern high-rise design to reduce mechanical cooling loads. Engineers in Jordan and across the Middle East are studying Nabataean decentralized collection systems as practical alternatives to large dams that lose massive volumes to evaporation. The iron pillar's phosphorus misowite passivation mechanism is being studied for potential applications in long-duration infrastructure, achieving corrosion resistance without expensive chromium or nickel alloys. The Lycurgus Cup's nanoparticle color shift principle now informs development of modern plasmonic sensors for medical diagnostics and chemical detection. Scientists studying Polynesian wayfinding are developing AI systems that interpret ocean swell data for autonomous marine vessel navigation. The Hokulea revival demonstrates that recovering ancient techniques yields both cultural reconnection and actionable scientific data. The design philosophy of treating impurities as assets, embracing phosphorus, volcanic ash, and slag challenges modern manufacturing's reflexive drive toward material purity and may produce better performing materials. Susong's constant level overflow tank solved mechanical pressure drift with a simple notch, an engineering principle still relevant in modern hydraulic and fluid systems. In cooling, water management, corrosion resistance, and structural durability, ancient solutions are demonstrably more efficient or longer lasting than their modern replacements in specific contexts. The next generation of engineering breakthroughs may come not from inventing entirely from scratch, but from listening to what the ancients already solved. None of these technologies broke the laws of nature. They mastered them. Every innovation on this list used fundamental physics, chemistry, or biology that existed then, exactly as it exists now. The difference was method. Centuries of patient observation, empirical refinement, and intergenerational knowledge transfer rather than theoretical models. The same oral and artisanal systems that created these peaks were the systems most vulnerable to disruption. Modern science has explained many of these technologies but still struggles to replicate several of them under original conditions. South Indian smiths achieved nanostructures. Roman glassmakers achieved plasmon resonance. Neither knew the name for what they had done. Many ancient technologies prioritized durability and sustainability over speed and cost. Values the modern world is now being forced to rediscover under environmental pressure. The core lesson is this: knowledge is not permanent. It must be actively maintained, transmitted, and defended, or it disappears within a generation. Technologies survive not because they are brilliant, but because the institutions that carry them endure. I would love to hear your theories. Which of these 10 technologies surprised you the most? Which one do you think we should do a full, dedicated, deep dive on? Drop it in the comments. And if you made it this far through the whole thing, thank you. That means a lot. If you enjoyed this, please like, subscribe, and share it with someone who would find it interesting. We do evidence-based, curiosity-driven content that respects both ancient achievement and modern science, and there is a lot more coming. The laws of nature never change, we just forgot how to listen. Thanks for watching, stay curious, and see you in the next one.